Hello, everyone, and welcome to the second webinar in our ICP Alley Road to Pittcon series. Thank you for being here. I'm going to give people probably maybe 15, 30 seconds to start rolling in here. I know it's 2 o'clock on the dot, our time, so give people a couple seconds.
So if I go to my share,
All righty, cool. Looks like good number of people coming in. I will go ahead and get it started. So thank you all for joining. Again, this is our second webinar in the ICP Alley Road to Pittcon series. Just getting everyone together for our ICP Alley at Pittcon, which will be here before we know it in March. So come stop by and see us. We'll all be together in our own little section called ICP Alley. So that'll be nice, easy to find us. Just a few little housekeeping details before we start getting into everything. There is a Q&A box at the bottom of your screen. If you have any questions, please put it in there at the end of everyone's presentation. We will transition into a Q&A section so we can get to your questions and answer all of them. If we do go over time and are unable to answer all of your questions, we will do a follow-up email, which will include any additional questions that we weren't able to get to, answered by everyone in this call today. The webinar is recorded and will be uploaded to YouTube, as well as Zoom's video program where you can use the link to watch there. That will also be included in the follow-up email, so that'll be there for you as well. And then, of course, if you have any technical issues, please reach out to me in the chat, and I can try to help you in whatever way I can. But yeah, without further ado, I want to thank everyone for joining me today. We have Michael Howie from CEM, Justin Masoni from Glass Expansion. Unfortunately, Ryan was unable to make it due to the snowstorm that is currently impacting the northeast of the country. But we're very lucky to have Justin to take his place. We have Mike Fearis from GFS and Thomas Kozikowski from our very own Inorganic Ventures. Thank you all for joining. And without further ado, I will turn it over to you guys. Michael, I think you're up first. Or sorry, Michael, yep, Howie.
all right, sounds good. Thank you, Chris. And we are going to go ahead and get started with our portion of the show today. Thank you for taking the opportunity to join us. As Chris mentioned, this is part of our ICP Alley initiative, as we are all going to be present at Pittcon 2026 in San Antonio. And so I'm going to jump into the microwave sample prep section, and we're going to discuss a little bit about why the microwave is a good option, but then also show you a few different configurations that CEM can provide for you. So one of the first things that we always like to talk about, and is very simple, and if you've ever seen me do a presentation before, you've heard me say it again, the solution is a solution. At the end of the day, you're trying to prep a sample, get a nice homogeneous solution so that you can then put it on the OES or the mass spec. And so that's why we do digestion to begin with. So what about pressurized? Well, we all remember from chemistry class that relationship with pressure and temperature. By simply pressurizing our vessels, we're able to take something as simple as nitric acid that boils at 125 and then run it routinely at 200 degrees Celsius and even up to 250 degrees Celsius. And what this does is that this greatly enhances its oxidative potential, giving us the ability to get a quality digest without the need perchloric acid, hydrogen peroxide as well, even reduce some of the uses of sulfuric acid. So why do we do microwaves? Well, much like you do at home, if you heat up water on the stovetop versus putting water in a microwave, why do you do that? It's easier and it's faster. Pretty simple. This is no different. This is why CEM is in business to provide rapid microwave pressurized digestions to give you good digest quality to enhance your reproducible data. So let's jump into the first system that I want to talk about. This is our latest system. This is a multi-mode or a batch system. It's called the Mars Express 2.0, and it allows us to do up to 40 samples at a time. So that is a great time savings. Um, and with our Mars Express vessels, this is the most popular vessel on the planet. And we are talking about from 20 milliliter up to 110 milliliter internal volume. And we'll talk about volumes and why that is critical because we want headspace so that we can accommodate for that pressure that we are generating from our digestions. Then also, I'm going to mention a brand new vessel that we're excited about called the Mars Express Max. And leaning back on volume, this is now 130 milliliters of volume. So the next thing that I want to talk about, as my slide goes here, is some of the more common applications for the Mars Express family. As you'll see, is that these applications range from your environmental, foods, fertilizers, through some of your consumer product testing. And basically, these are the laboratories, the high throughput testing facilities that are just churning out hundreds of samples a day. These are the types of applications that the Mars Express shines. Routine, and for us, moderate temps and pressures of about 200, 210 degrees Celsius. This is the ideal workhorse for that. And again, by doing up to 40 at a time, you're maximizing your throughput capabilities. And I'll mention it later, but with the US EPA, there is a microwave methodology known as US EPA 3051A. And this, you can run up to 24 samples simultaneously in a 10-minute microwave run, as opposed to the hot plate, hot block methodology of 3050. All right. So I mentioned the Mars Express Max vessel. This is our latest vessel. And what we've done here is we've taken a 24 position turntable. We've increased the volume from 110 up to 130 milliliters. So you may not think that sounds like a lot, but it's about 20% increase in internal volume. And then what this does is that volume helps us in the reaction gas, the pressure, and managing it. So by having the more headspace, it's cooler. It's even cooler up at the top, which does reduce the vapor pressure inside of the vessel. So what does this mean for you as a user? Well, so in some of these food samples, let's say you need to increase your sample weight due to detection limits. This is a great vessel for that because now, you're accommodating a larger sample size. And then with 16 vessels, as opposed to 210, we now can do 220 degrees Celsius in this vessel because it does make sense. You put in a little more material, you need a little bit more temperature to get the digest done in the same amount of time. Now, one thing that I will mention is that for Pittcon, we are going to have a mixed foods application note, and this will be available at our booth 2659. Okay, so the next vessel that I want to talk about and its applications is our easy prep vessels. So I'm big into automobiles. So, it's the right car, the right tool for the job. So with our Mars Express, that's our daily driver. It's doing all the chores, it's getting all the kids to school and practices, getting you to work. Now, now I need something to do a little more towing, maybe. Okay, I need to throw some gravel in the back of my truck. So I need a different vehicle. So with this Easy Prep vessel, what we're doing is now we're upping the ante. So we can do all of the same Mars Express applications, but now we kind of move up the food chain when it comes to the complexity of our matrix, such as some of your polypropylenes and polyethylenes. Definitely can do some waste motor oils. In this vessel right here, if you live in the space of inorganics, exotic materials, this is the vessel for you. It is really good for ceramics and alloys, things that require high temperature hydrofluoric acid. None of us want to do it, but sometimes the chemistry demands it, and we can still use that HF at super high temperatures here. All right, so our next vessel that I'm going to mention is the iPrep. So if the other one was a pickup truck, this is going to be the bulldozer because when it comes to high temperature, high pressure applications concurrently, the iPrep vessel is it. Very simple to assemble. You can do up to 12 vessels simultaneously. And you'll see here in our chart, this is where we've done like polyethylene terephthalate, bunker oil, Kevlar. Kevlar is notorious, a pretty rugged material, and we do that with 10 mils of nitric acid at 240, 250 degrees Celsius. And with this, it's really good for something like a rhodium catalyst because you have to take hydrochloric acid up to about 240, 250, and that acid alone generates in excess of 800 psi just in vapor pressure. No reaction gases generated, simply the vapor pressure at that temperature. Um, so we will also be presenting an oils and plastics um, presentation at the Pittcon Symposium. And right here, you see the date and the time and the room that I will be presenting that as well for more information on iPrep applications. And the last system that we're going to talk about, we're going to mention is the blade. So this is a system that came out a couple of years ago. This is as opposed to, oh, wait a minute. I went back too many slides. So with the blade, as opposed to a batch system where you're doing up to 40 simultaneous, this is a single mode sequential system, meaning each vessel is digested one at a time. And then the automation brings it out, puts it back into the rack, and then moves on to the next sample. And so what some of the cool stuff here is that we do have a camera. There's vortexing of your sample while it's being irradiated with microwaves. And then also with that diversity of having a sequential feed, now you can have 24 vessels that have 24 different samples, 24 different acid matrix, and create and just do a whole library of samples all in one queue. Our vessels, you'll see here, that is a high purity quartz vessel with a stir bar, a simple snap cap. And then over here, we also have, you'll see a TFM liner. This TFM liner, we will put that inside of the quartz vessel to allow you to perform any HF applications. Also, any phosphoric acid applications, as that will attack the quartz as well. And this is just an illustration of a rack of 12 vessels. And it's got 12 different samples. You could not do this in a multi-mode or batch system. Here you could have 12 different chemistries. The blade will accommodate up to 24 positions in a queue, averaging probably about 10 minutes a digest. And so this is one of the things that's kind of a cool feature with the blade as well, is that there's a camera. So you're actually looking at the digest happening in situ. And so right here, you've got 6 different battery materials that we digested. And these were all done in the same sample queue, one after the other. Completely different acid chemistries, different methodologies as far as temperature, but you can see that we are recording the temperature and pressure, and you do get that cool feature of being able to actually watch the digest happen in real time. All right, so basically, in conclusion, what we're just going to say is that microwave digestion is the way to go for sample preparation. It provides you with the highest quality digest and to generate reproducible data because at the end of the day, that's what it's all about. Nobody on this webinar right now raises their hand and says, I can run a microwave on my resume. Everything is about the analysis. So our job is to make high quality, reproducible sample preparation so that you can go do the other part of your job with the analysis. And so we've covered a few different options, and we are always here. We've got a team of 5 application chemists to help answer any questions and to provide extra guidance. And other than that, you can always join us on cem.com for application notes, including the application notes that will be visible at Pittcon. We have a email support system. I'd like to always point out a couple of interactive periodic table that Inorganic Ventures has. It's a fantastic tool for dissolution and then also some OES and mass spec tips and tricks on there as well. And we have a periodic table. And then we also have some in the lab videos on our website. And it's our actual chemist in the lab with a brief 1 to 2 minute um, tip and trick on how to weigh out a sample or how to get static stuff down into a tube. So I want to thank you for your time. And I'm going to go ahead and hand this over to Mike.
Thanks, Howie.
I'm off.
I think you still need to stop sharing there, Howie, so that I can take control. There we are. All right. We're going to talk about some better solutions for cleaning your labware. So it was nice there, Howie pointed out multiple different types of vessels that are there with the different microwave options, because that's really what we're going to be talking about when we're talking about your labware, that your beakers, your flasks, anything like that. Because that's going to be a component that goes into your final results. Whatever you're getting from that labware and any contamination that may come out of that. So we want to get those cleaned up as much as possible. So your labware materials, they may be some sort of glass. There's benefits to that. Long-term cleanliness, you're going to get the same levels of contamination throughout all of them. It's going to be low on carryover. However, they are fragile. They do have a consistent baseline. So if you get some low quality glass, that can be problems for the entire time that you have them. And they're not capable of handling all the acids, which is why they pointed out the TFM inserts for your HF and phosphoric acids. Your plastics, they can be a little bit harder to clean. You may have to do more intensive cleaning each time. You might be dealing with HDPE, LDPE that are pretty durable. They're versatile. They're really cheap in comparison to others. And then they may have some trouble with long-term stability, particularly with a nitric acid. They generally have some pretty strict 2-year lifespans on them. But then as you move into your more expensive plastics, your Teflon, PFA, FEP, things like that, they can be very durable and long-term compatibility with acids. So you can keep, even nitric acid in there for years and not really see a degradation in the quality of the bottle. But they are also much more expensive than your HDPE, LDPE, an order of magnitude more in some cases. So, when we're talking about cleaning them, glass, it's going to be really easy. Usually some sort of surfactant, dilute acid, rinse it off before you go back and start using it for samples. But that baseline, however that quality of glass is going to be what determines comes out of it. If you have lower quality glass with a lot of impurities, you're going to always get those things out. Boron, maybe aluminum, things like that that might be in the grains in there that will come out as you put your sample in there. But then as you get to your higher quality, you can get some very high purity quartz. We use that for a variety of applications in our lab, and we get contamination on the level in the parts per quadrillion for even some of your really tough things, calcium, sodium, potassium, iron, all those environmental things that may be problematic in other places. But in general, if you get some high quality glass, high quality quartz that you can get results out of continually, they're going to stay pretty consistent through the life that you have them. Now, plastics, your HDPE, LDPE, most bottles that you're going to get for, your trace metal acids, things like that, they're going to be made out of this. They're very good in the short, mid-term for storage. They can be very clean. You can get relatively high quality HDPE, LDPE right away. PPB levels of detection, even less. Low PPT levels of contamination and at a very affordable price. So that's something that's in a lot of labs as flasks and things like that. But they are porous, so you may have a little bit tr of trouble cleaning them up. Uh, Run to run, you have a little bit of carryover. Uh, Usually, some dilute acid works in a matter of hours or even less in some cases. You may have to use a little bit of a surfactant depending on what type of sample you had in there before, whether you need something non-polar to clean that up. And then one of the little watch outs is that when you do have high exposure samples, something that's an order or two of magnitude above what you're typically working with, you may have to do multiple stages of cleanup sometime over the course of weeks, or even in the worst case scenario, it may take months, or in HDPE, LDPE case, at that point, you may just swap it out for a new piece of labware. Teflon, your PFA, FEP, PTFE, all those, you're going to have it's a much more expensive piece of plastic. You're going to rarely throw that away, but it's going to keep that long-term durability as well. And again, a lot of it's dictated on the quality of resin, the starting material. Sometimes we've come across some manufacturers that give you into the single-digit PPT level of contamination right away without really having to leach anything out of it. But then again, as you use over and over, putting samples and contamination in it, you're going to have to continue cleaning that up. Um, and they do have, like I said, great long-term durability. There are some watch outs if you are storing HCl at a high concentration in there, somewhere around 36, 37%. You're going to see some scarring in it. And that's kind of where the HCl partial pressures in the container actually force its way out through the pores in that plastic. And you see this cloudiness to the bottle and actually a rougher texture on the outside. And that's kind of all due to like these pores and the way that things can get through and even get stuck in there, which is why, similar to that HDPE, you may have intensive, longer term cleanups on these when you do have that higher levels of contamination, or when you're going to those elevated temperatures. How we pointed out, some of the methods there are getting up above that 200 degrees Celsius. When you are getting into those, particularly that first time and repeatedly, as you get, again, those couple of orders of magnitude away from your typical, you may have to do a lot of extra cleanings, some more intensive cleanings. Sometimes it'll take 5, 10 cycles of even heated, elevated temperature cleanings before you get back down to maybe a low parts per trillion level of detection limits. I had somebody reach out to me kind of with this same kind of question. They hadn't realized that the porous plastics can hold on to contamination very long and do need much more intensive cleaning practices, particularly when you are working with them regularly at those much higher temperatures. So, and when we're looking at these porous vessels and kind of how they hold on to things, this is what it can kind of look like. You have your nitric acid dissociated into ions, some sodium kind of sticking in the pores of our, makeshift PFA beaker here. And then they're going to kind of cling on to those sodium atoms and pull them out of that plastic in a leaching process. And then we're going to rinse it out and repeat. And then ideally, you have a much cleaner vessel than what you started as. So here's kind of what that reaction is. It's a simple like mash reaction. A metal and an acid are going to yield a salt and hydrogen, but typically at such a low level, you're not going to see a lot of hydrogen coming out. But it's kind of the chemistry behind what's happening when we're talking about cleaning up plastics and leaching. So. Just kind of wrap up. Really, you just need to be more familiar with your labware, what types you're working with, and knowing what the best cleaning procedure is, and making it a regular habit. And if you are seeing repeated issues, please reach out to us. Collaboration is one of the greatest tools you can have, and that's something that we all here enjoy. We love hearing from you guys. So. If you have any questions, reach out to any of us. Here's my email. I'm sure it's in all of the other promotions for this. So uh, I'll now hand off to, I believe, Thomas, correct?
Yep, that sounds right. Thank you, Michael.
Hmm.
Let's see. All right. Well, thank you all for joining us today. My part of this is I'm going to talk about the benefits of a custom CRM. So a little bit about Inorganic Ventures and our CRMs. We've been around since the 80s, making stock singles for years, going into the custom multi-element business. So we've got a huge catalog of products ready to go, but we also have a lot of customs. So all of these are ISO accredited, 17034, 17025. We're also 9001 registered. All of our products are NIST traceable. We use NIST standard reference materials for calibration and direct comparison when possible. And there are a couple that we are doing ourselves for example, osmium. We trace that gravimetrically to the SI ourselves. We have over 63,000 unique solutions available for order, and we're adding approximately 10 to 14 new solutions daily. So why not just use stock products? Well, there's a bunch of reasons where a custom might be better. First of all, you can avoid potential interferences. Another is washout time for unnecessary elements. You might have something in your standard you just don't need, but it's affecting something else. Matrix matching capability. Our stock products are pretty much fixed. You're going to either get nitric, HCl, or a little bit of HF, but might want to change it up depending on your application. Customs can come into play here. And of course, reliable, accurate, and stable for years. Our custom products have gone through a lot of testing to make sure they're good for the expiration that we give it. And in some cases, they're ready to use. You can get a custom that's, a concentrate that you make your own dilutions, but you can also get them pre-diluted, which would save time for your analysts. So here I've got a little interference example on our OES. You should consider, a custom internal standard mix if it's affecting some of your, your analysis elements. So this is iridium. Looking at the 212 line, you'll see that yttrium being used as an internal standard is actually going to cause a problem on this line, and you won't be able to use it. Here, you would probably want to. There's only two good iridium lines. So those of you in the precious metal industry know it's one or the other. Otherwise, you're going to have to switch to mass spec, and even on that, you've only got two choices. So if you wanted to try to, use an internal standard for this, we would need to take yttrium out. And so a custom might be a better option here, where you can pivot to a different element and it wouldn't directly interfere on this line. On our mass spec, IV stock 25 is a very common internal standard mix. It contains bismuth, germanium, indium, 6-lithium, lutetium, rhodium, scandium, and terbium, all the same concentration. Let's say I want to test selenium in HCl, but I can't use a collision reaction cell. So there are a lot of folks that use certain EPA methods where it disallows that use. So we might have to play around with a custom to get this to work. We would like to use more than one mass if possible. Selenium is already not very abundant if it's very spread across multiple masses. So if you look here, I've got the isotope chart. You'll see that 76 selenium has an isobaric interference with germanium, our common internal standard element for this mass range. 77 has an argon chloride. 80 has a double argon, but also scandium chloride. Scandium's used for a little bit lower mass range. And then 82 also has the scandium internal standard issue with chloride. 78 looks good, but again, we don't like it when we can only look at one mass. To get better confidence in our results, we'd like to look at more than one. So what if I swapped out germanium for gallium? You'll see that those don't interfere on the selenium masses. I wouldn't be able to check rubidium, but if I don't care about rubidium, we'd be good to go. So I would highly recommend you look at a custom in this case, because also you can get rid of HF from the solution. A lot of folks don't want HF in their analysis, so this would be a way to rid that, because germanium is the only one that needs it in this case. Another issue, washout. So if we've got two common standards here, our IV ICP-MS 71 series, the B solution has all of our HF elements, and our C solution has all of our precious metals. We're going to also throw mercury into this mix. We keep those separate for stability reasons. Let's say for this analysis, I care a great deal about those mercury results, but it's taking a really long time to wash out after running my standard, but my sample washes out quickly. Looking into this, I need some of the elements from 71B, but not all of them. I'm trying to get away with the cheaper stock option, and try to get everything done, but I'm having some washout problems. So in this case, tungsten is actually our issue. So tungsten oxides on our mass spec are causing issues on the mercury masses. So if you look at this chart, you'll see that every single tungsten interferes with the oxide on every single mercury except for one. So 201 is the only mass without a direct 16 oxygen interference, but we still could have an issue from 18 oxide. Not as common, not as abundant, but it's still something to keep in mind. I don't need tungsten in my standard. I'm looking at my analysis and like, I don't care about tungsten, so I should remove it. Another issue is, it's actually sticking to the plastic. So I've got this, and if you've ever watched my washout webinars in the past, this is a little snippet from that chart. Even with a peri pump or the syringe drive system where it doesn't touch PVC, tungsten lingers for quite a while. So this is 3 different rinses and you still have counts. So if I had to remove this completely, there's no issue and mercury is much happier. Of course, mercury has its own washout issues, but HCl usually does the trick. Next up, we've got standard matrices versus custom options. So our stock standard matrices, you'll see this chart from the last time we did this ICP Alley webinar. HF elements here in the yellow. There are some options where we can put titanium, zirconium, tin, antimony, and tellurium in HCl instead. So that's why we've got the blue box around these. And then molybdenum, tungsten, and silicon, those HF elements can be done in a basic media. So if you have the capability to run this in base, you're probably caring more about bromide and iodide, but the option's still there. When you look at the HCl chart, we do have rhodium, palladium, platinum, and mercury available in nitric acid. So if you're looking to mix these with silver, we do have a way to do this chloride free. Keep in mind, though, if you need the mercury at lower levels, you would need to switch to glass, and that can pose other contamination risks that Michael didn't cover. He covered plastics, but yeah, glass can be pretty dirty. unless you get high purity quartz, which is pretty cost prohibitive when it comes to bottles. Um, but these are, matrices, we've got options. So if something doesn't work with the stock, we might be able to fit it in with a different custom solution. Now, a little bit more about our custom standards. Our standards are made gravimetrically to boost accuracy. So we are weighing these on a four-place analytical balance using certified stock single solutions. Our custom CRMs are produced under our scope of accreditation, so consistency is maintained through audited work instructions. Our densities are determined so that the user can switch between weight to weight or weight to volume units. So a lot of labs like to do it differently. We give that, the ability to switch between the two. So if you desire. And then standards are guaranteed homogeneous and stable for 5 years. So if you've got a really, really strange request where our quoting chemists are not quite sure if it's going to work, it might be testing the limits of what we're comfortable with. We'll give it a 1 year expiration date and put it in our stability program to monitor over the desired 5 year period. So we'll monitor that yearly and make sure it's still okay. And if it is, we'll extend the expiration date. And then future times that you would purchase that product, it would have a longer expiry. Next up, reliability. So your results are traceable. You have an unbroken chain of comparisons to the NIST SRM 3100 series, but also the wet methods when possible. So a lot of our single element standards are certified with a wet method. Think EDTA titration, gravimetric assay with the sulfate precipitation. Many different ways to get a second method. So it just boosts the confidence in that single element standard, which we then dilute down gravimetrically so that we have that unbroken chain. All of our customs do come with documentation, so the C of A will tell you how to use your standard, what it's traceable to, all the things that your auditors are looking for, whether it's EPA audits or whatnot, pharmaceutical. They typically are made within 0.5% of the desired nominal value, and the uncertainty values are just as low. And we typically are able to manufacture and ship these within 2 weeks, and we do have rush manufacturing available upon request. Another thing, I mentioned this before, you can get standards that are ready to use. So a calibration set will take time to make at the bench. That's just extra labor, time that you could be spent doing other things, and analysis. So ready to use customs for your calibration method can save time, reduce the risk of contamination, since you can simply pour from the bottle instead of pipetting multiple times from the same bottle, which again, our certificates strongly discourage. But some of us might do that anyway. Just remember, every time you put a pipette tip into a bottle, you're transferring from that polypropylene tip, possibly calcium, magnesium, and I've seen aluminum. You're just concentrating that in your bottle over time, unless you pre-leach those tips. You can also purchase multiple years worth of your standards and enjoy the same lot long term due to our TCT packaging. So finally, a little bit about our transpiration control technology. We call that TCT. It allows you to buy larger volumes in series of smaller bottles. So you can get the same lot. If you know exactly how much you're going to use, you can get, much better pricing when you order a bunch at the same time. But you can still have a really long expiration. So that 5 years is for the lot after we manufacture it, and it's a year after you open the bag. So make sure you don't open the bag, of course, until you need to. But this will help you maintain that same lot, even for a custom solution. It'll reduce your contamination potential because you'll be using the bottle less frequently. So you'll pour out of it straight into your tube. You won't have, the pipette going in and out. But you can control the expiration of your inventory. So you open maybe one bag per year. You can buy 5 bottles. You can use the same lot the whole time, and you'll have good confidence to know that from year to year you're still getting the same calibration curve since day one. Now, keep in mind, TCT is not the only way to slow transpiration. You can if you need to extend the life of your standards, you can refrigerate these bottles to stop transpiration. We've got extensive data on that. Check out our website for that. But always remember to return to room temperature and mix very well before use. That density, of course, that we report on the C of A is based on the room temperature of that bottle. So the density will change upon heating or refrigerating. So for that to be, in spec, you got to bring it back to room temperature before pipetting. Of course, you can scan this QR code to navigate to our TCT education page for more information on how this works. So I'm not going to, use any more of your time. We do offer more than just custom solutions, of course. So check out these 3 codes. We've got IV Ignite, our official virtual training academy of Inorganic Ventures. We also have Bench Boost Podcast, which releases a new episode every Tuesday. You can get that on Apple Music, but also Spotify. And then our website, of course, is free educational resources for all chemists, whether you're a customer or not. So make sure you scan these codes, check out our website. And if you've got any questions, feel free to ask us anytime. So with that, I think we're going to kick it off to Justin from Glass Expansion.
Thank you, Thomas. All right, let's make sure I can share my presentation. Okay, and for anyone who joined late and didn't hear the introduction, Brian will not be joining us. He's still digging himself out of 3 feet of snow, so I'm taking his place. So today we're going to be looking primarily at nebulizers, just a brief overview of the factors that contribute to their performance, how to optimize them, why you might want to select one over the other, how they form an aerosol, and how that affects your analysis. Also, I'm sure most of you are familiar with glass expansion, but if not, we have a larger library of support materials and literature on our website. So just as an example of why nebulizer selection, really all sample introduction accessory selection is important, is because there are a bunch of different types and there is a correct choice or an optimal choice for your sample type, for your analysis, for your requirements. And as an example, this is a comparison of nebulizers available from Glass Expansion. This is sort of just more of a comparison chart. We've got the glass nebs up top, sea spray, micromist, conical slurry, the quartz sea spray, and then plastic nebulizers below, the opal mist and the duramist, and then our ceramic V spray nebulizer. No need to copy all this down. We're starting it. This is available on the GE website. Anywhere you get a nebulizer from, through an OEM, another third party, they're going to have a similar chart. And this just shows you the differences in, for example, tolerance to dissolved solids, tolerance to particulates, tolerance to HF. Is it a high precision nebulizer? Is it something more for really dirty samples and you just have to get a result? So again, just an example of all the different types of nebulizers you can get for your system. The way we number our nebulizers, it tells you about the nebulizer. So the prefix, in this case A13, that indicates the instrument type that this white connection on the end of the gas line goes to. This will hook up directly to a specific instrument. Previously, they started with ARG, and that was just universal nebulizer type. So some people might still have boxes in the lab that say ARG. That's just the older style connection. So A13, the first 3 digits, that's going to be the instrument specific model. The middle number, typically a 1 or a 07, that indicates the nominal argon flow for that nebulizer. Now, the way we do it is that at this argon flow, in this example, 1 liter per minute, that will produce 40 psi back pressure in this nebulizer. And then the last part of the part number will tell you the nebulizer type and the uptake rate. So in this case, that means micromist. You can see the other abbreviations below that. And then 0.4, that means it will self-aspirate at 0.4 milliliters per minute. Another interesting thing to think about is that now most people do use a peristaltic pump, so you can control the sample uptake rate. You can dial it in depending on the pump speed and then the peristaltic pump tubing size. But if you're doing self-aspiration, and there are reasons you may want to do self-aspiration, if you have a question about that, feel free to ask. You can adjust the sample uptake rate when doing self-aspiration just by changing the capillary tubing. So for example, this micromist nebulizer, A13-1UM04, so that's a 0.4 mil per minute micromist. It's supplied with 0.5 millimeter ID capillary tubing. And that will self-aspirate at 0.4 mils per minute, or around 400 microliters per minute. But if you decrease the capillary tubing ID, you can get a subsequent decrease in self-aspiration uptake rate. And there's no formula for this. This is something that has to be done by experiment. But if you're doing self-aspiration and you've got a nebulizer that is designed for, let's say, 0.4 mils per minute, but you want to self-aspirate at a lower flow rate, you can just use a smaller sample tubing capillary ID. Just a quick note on basics of aerosol generation. This sort of explains how aerosol is formed and the components or the factors that play a role in that. And this is important to understand why you pick certain flow rates, certain gas flow rates. So the primary aerosol is produced by the nebulizer itself. The tertiary aerosol is what comes out of the spray chamber and goes into the plasma. The spray chamber is really just a filter. It filters out droplets that are larger than about 10 micron. Typically, for the best sensitivity, the best performance, you want a much smaller and more uniform droplet size. This requires less energy from the plasma. If a droplet is too big, it'll go all the way through the plasma without going through the stages of vaporization, desolidation, atomization, and then ionization. And typically, the way you get a much smaller average droplet size and a much broader range is to use a lower flow rate and a higher gas rate. So just an example of the effective nebulizer design and sample flow rate. So in this case, we took three nebulizers, a V-groove, a large bore concentric, and a high efficiency concentric. Kept the net gas flow at 0.7 liters per minute. And you can see how certain nebulizers will give you a higher percentage of droplet sizes less than 10 microns. So that single digit micron range is where you want to be to actually analyze what's coming out of your nebulizer. And just continuing with the same theme, we're looking at average droplet size for, again, three nebulizers. In one case, a V-groove, another one a large bore concentric, and another case a high efficiency eccentric. So on the y-axis, we have average droplet size. This is called the Stauder mean diameter. So it's a way just to measure droplet size of the primary aerosol. So you'll notice that on some nebulizers, on V-grooves, again, those are nebulizers that are designed to let just a bunch of particulates through, but you don't have a very good small concentration of analyzable droplets. Compared to, on the right-hand side, we have a high-efficiency concentric nebulizer. So this is something that is going to be designed to operate at a somewhat lower flow rate than some of the other nebulizers, not as tolerant to particulates, but it's going to give you the absolute best aerosol concentration. On here, we have the relationship of back pressure versus gas flow rate. So this example is from a 1 liter per minute nebulizer model, in this case, A13-1USS04. We vary the gas flow rate from 0.5 to 1 liter per minute. And again, this one in the middle, that means at 1 liter per minute, we should see about 40 PSI of nebulizer pressure. So this is the optimal value for this specific nebulizer. You want to keep this at 1 liter per minute if you have a 1 liter per minute nebulizer flow rate. So the reason that's important is because this we see right here what the actual effect of the nebulizer gas flow rate has. Again, a 13.1 USSO4, so a 1 liter per minute nebulizer. And we're looking at the percent of droplets smaller than 10 microns. So again, we want to have as many droplets as we can in that single-digit micron range. So if we decrease the gas flow rate beyond what the optimal or value is, in this case, 1 liter per minute, you see that the percentage of those droplets that we want drops off significantly. And this isn't much. So at 0.8 liters per minute, we're at less than 50% of the aerosol is that ideal droplet size, compared to what looks like 65-ish% at the 1 liter per minute flow rate. So that's why you want to use the correct gas flow rate for your specific nebulizer. I don't want to cut into our Q&A question, so we can just come to what I think is a pretty important slide, is just how to keep your analysis running. Nowadays, everyone pretty much knows or knows where to find the information of how to select the best nebulizer, the best sample introduction system, how to do the prep work. But what we want is an instrument that we could just set up and run and walk away and let it run for 3 hours, 4 hours, 6 hours, 8 hours, and not have to worry that we're going to have an issue and come back and have to rerun everything. Two accessories that are worthwhile having. One is the LUL nebulizer cleaner. This is designed for GE nebulizers. It's simply a back flushing device. Every now and then your nebulizer might get clogged. There's a whole cleaning procedure online, so I don't need to cover it up right now, but basically you draw up cleaning solution in that syringe, lock in the nebulizer, and back flush it. That's also something that just should be done as part of routine maintenance, just to make sure your nebulizer is in optimal condition. And then down below there, we have the Allegro carrier gas humidifier. This is something else that I think most labs can have. What this does is this humidifies your carrier gas. So if you're running high solids, and it doesn't even have to be high solids, if you have any amount of dissolved solids in there, those will build up over time. There's no downside to using the Allegra. It doesn't dilute anything. It just hydrates the carrier gas to prevent any sort of salt deposition at the tip of the nebulizer or at the injector. So just, again, for peace of mind, you know your instrument's going to be running at the optimal level for your entire analysis. So with that, I will pass it back over for our Q&A.
All righty. Thank you so much, everyone. So yeah, we got a little bit over 5 minutes we can start the Q&A. And of course, like I mentioned previously, any questions we aren't able to get to will be followed up in a Word document and sent out to everyone who registered. So without further ado, our first question we will go to is, can Express Systems handle HF? And I believe that one is for Michael H.
Yeah. So I guess what we're looking at is the Mars Express 2.0, but more importantly, the Mars Express vessel. So yes, you can perform hydrofluoric acid in the Express family of vessels. There is a little bit of a caveat there, is that these vessels by design are a vent and reseal or self-regulate. So they vent off pressure as it builds up. So with this particular vessel set, we do have a recommendation of not exceeding 180 degrees Celsius with HF. But any and all US EPA 3052 type applications, you can certainly perform in the Express vessel. Good question.
All righty. Our next one is, can the blade prep be done without a stir bar? And what parameters would you adjust if possible without a stir bar?
Okay. So the blade microwave system, you must have stirring in there. We use stirring for a variety of reasons. Not only does it help pull the solid mass down into the vortex, this way we've got maximum coverage, maximum surface area exposure to the acid. Um, Stuff that floats like filters, pellets, it helps pull them down into the vortex so they don't sit up there and float. And then also during our cooling, we actually turn the vortexing up even more, and it helps to spread that volume up and thin it out to have a more rapid cooling. So in short, there are no parameters to change. You have to do stirring using the blade.
Great. All right. The next one is from another attendee. It says, we have a blade digester, and they had a couple questions. If their standard matrix is 2% nitric acid and their blade allows a minimum of 5 milliliters to be utilized, and if the final dilution is 50 milliliters, that accounts for 10% of the nitric acid. Is there any way we can add a minimum of 5 milliliters, keeping the final nitric acid 2%, like addition of peroxide and water? Sorry, that might be one that's best read on best seen written.
Okay. All right. So I think I've got it. But in short, if you're trying to be very specific with your acid concentrations, whether it be from diluting it in the vessel or even your stock solution forward, yes, adding some water, potentially some peroxide based on the matrix. I would love for you to actually communicate with our support team for that. But yes, you can add a little extra volume of water to get that minimum of 5 mils that is required by the blade.
All right. And the second part of their question is like Mars 6, where we can see a graph of tubes that were run and how each tube reached so temperature and pressure. Can we check the consistency of tubes that run in blade? That makes sense.
Absolutely, and that's actually one of the even better features that you have in the blade compared to the Mars 6 platform is that every single vessel, every single digest, you get a full analysis of pressure, temperature, and power graphed. Then you can even get both a PDF and a CSV report for each individual vessel that is run.
Great. All right, our next question is for plastic/Teflon vessels, would you recommend an acidic detergent cleaning solution, for example, Citronox, or a basic one like RBS-25 when being used to dissolve metal alloys?
I think this one's probably mostly for me.
Yeah, go ahead.
Yeah, typically, I would say, yeah, you're going to want to use an acidic detergent, but it'll depend on what elements and metal alloys you're dissolving or need to leach out of those plastics and clean out. I know IV has had some presentations that mentioned best uses for, I think, RBS-25 for removal. What were some of those elements there, Thomas?
It kind of reconditions the surface of the spray chamber. So we actually got this tip from Glass Expansion. Yeah, so it works really well with conditioning the glass, but also like the coating on those PTFE spray chambers. But it does work extremely well for organics.
All right, and this next question I know was added at CEM, but maybe Thomas might be good for you. What is an alternative to CCS6 to have without CD, PB, and HG?
Yeah, so
Oh,
CCS6 has a bunch of elements in it at 100 ppm, and if you don't want cadmium, lead, or mercury, this is custom territory. So basically, just send in a request to us at info@inorganicventures.com and say, "Hey, I want CCS6, but I don't want these three elements." I just did a search for it in about 2 seconds here in our LIMS system. It does not exist, but it can exist. So just reach out to us and we can get that quoted for you.
Awesome. Our next question is from Tanner. Said, I've had certain samples with high amounts of sodium and potassium shut the plasma off while running, and their solution was to increase the RF power since they figured the matrix was putting too high of a load on the plasma. Is there another way to go about this in light of the glass expansion presentation about flow rates of gas and nebulizer flow rates? And why exactly would certain solutions cause the plasma to shut off?
Yeah, so I'll definitely follow up offline because we're running out of time, and this is a bit more. There's a lot of information to answer this question. To answer your last question, why exactly would certain solutions cause the plasma to shut off? Yeah, it's because it's overloading the plasma, and it's causing the plasma to cool too much. That happens with solvent loading, matrix loading. If you're putting too much solution there in general, even if it's just clean water sample, it's going to cool the plasma excessively to the point where it turns off. Other ways to go about this, just off the top of my head, again, I'll follow up. Dilution, lower uptake rate, using a baffled spray chamber. But again, there's a lot more to it. I'll follow up offline.
Great. All right. And I think we can do one more. I think this one might be short. And Thomas with IV mentioned that calcium, potassium, and aluminum were known to leach if pipette tips aren't pre-soaked. Is this for glass?
No, I was specifically talking about the plastic ones. So if you use like a rain-in pipetter, that's what we use when we do our aliquots. Those plastic tips do contain those elements if you don't pre-soak them. If you were to use glass ones, you're going to have different elements. We've got a whole list of things that comes out of glass. It's bigger than those three. But if you have any specific questions, feel free to reach out to us and we can cover that in more detail.
Great. All right. At that, we will call it a wrap. Thank you for everyone who reached out. Thank you, everyone, for putting on this excellent presentation. We will all be in Pittcon in, I guess, 2 weeks from now about. That'll be here before we know it. So come see us at ICP Alley there. As I mentioned before, everyone whose questions we didn't get to, we will follow up in a communication email that will go out within the next day or so. And that's a wrap. So thank you so much, everyone, and have a great rest of your day.
All right. Thanks, guys.
Thanks, guys.